You are clinging to the side of a tough, ribbed green stalk.
Mhm.
And the wind is just howling around you, whipping across this endless flat meadow.
Right, and it's bending the stalk back and forth in these violent, sweeping arcs. But you hold on tight.
You have to. You secure yourself with one single, incredibly muscular foot, just anchoring your body against that violent sway because you are tiny. I mean, no bigger than a human thumbnail.
And your heavy spiral shell is this perfect camouflage swirl of pale gray and brown.
Yeah, so you move your rough, scratchy tongue against the stalk. You taste the sharp tang of dried salt, and then followed by the rich, earthy flavor of a very specific fungus that you've actually been cultivating.
But if you look down, far below you, the ground is basically an alien landscape. It's dark, slick, and squishy, and it shines like black oil in the sunlight.
And it smells powerfully of sulfur, like a thick, heavy scent, kind of like a rotten egg left out in the blazing heat. But you aren't paying attention to the smell at all.
No, because you're feeling the vibration. A low, steady, rhythmic rumble begins to travel up the green stalk. The water is returning.
It creeps over the dark mud, this rising tide of murky, nutrient-rich green. And beneath the surface of that rising water, these massive, bright blue claws are snapping open and shut.
They're heavy, and they are sharp, and they are searching the stalks for a meal. They're searching for you.
So you have no choice. You must climb. You scrape your way higher and higher up the green stalk, just pushing yourself a few precarious inches out of reach of those snapping blue claws and the rising tide, settling in to wait out the flood.
It is a terrifying, high-stakes reality for a little climber. Basically, a daily physical game of survival dictated entirely by the mechanics of the ocean.
The margin for error is essentially zero, and what a game it is. Welcome back to Saltwater Stories.
We are so glad you're here with us.
If you are listening, the tiny creature you just imagined being was a marsh periwinkle snail. The monster below with the snapping claws was a hungry blue crab commuting in from the ocean.
And the setting for today's story is a place you have probably driven past 100 times without a second glance, the salt marsh.
Exactly. Our mission today is to completely change how you view this environment. We're going to see how this seemingly quiet, empty field of grass is actually a fiercely competitive metropolis.
It's a vital planetary shield and honestly one of the most mechanically complex habitats on Earth.
It really is. It's a true borderland, right? This exact geographical threshold where the solid, predictable, dry earth we live on just collides with the unpredictable, salty waves of the sea.
Yeah, but to really understand the creatures that live here, the snails, the crabs, the birds, we first have to understand the architecture of the environment itself.
Because the physical properties of the marsh basically dictate every single biological trick we're going to talk about today.
Absolutely. So let's build that visual for you. Imagine you are standing on the edge of dry land, looking out toward the ocean.
Right behind you is a normal terrestrial environment, like maybe a coastal pine forest or some tough sandy shrubs or even just a coastal highway.
But in front of you, the solid ground just stops. And suddenly, you're looking out over a massive, incredibly flat meadow.
In the slightly higher areas, the grass is short and swirly. It almost looks like a giant green cowlick pressed down by the wind.
I love that description. But as your eyes move closer to the water, the ground drops slightly, and the landscape is dominated by these tall, stiff, bright green stalks rising straight out of intensely dark, wet mud.
And cutting through this endless field of grass are these winding serpentine rivers of brown water.
Right. Those winding rivers are tidal creeks. You can think of them as the arterial highways of the salt marsh.
Because the salt marsh is defined fundamentally as a coastal wetland. It's an ecosystem that literally exists to be flooded and drained by the salt water brought in by the ocean's tides.
But the defining physical characteristic, and this is absolutely critical to why the marsh exists at all, is that you will never find a salt marsh on a beach facing huge, crashing waves.
I really want to highlight that distinction because it's so easy to miss. If you grab a surfboard and head to the beach, you are not going to see a salt marsh.
No, definitely not. A beach is a high-energy environment. The marsh is entirely different. It's like the ocean's quiet backyard.
Right, it has to sit in a sheltered area, maybe tucked carefully behind a barrier island, or deep inside an estuary where a freshwater river meets the sea. The energy of the water has to be fundamentally different.
And that low energy of the water is the only reason the marsh can physically form. The foundation of the salt marsh isn't heavy sand.
It's incredibly fine, almost microscopic mud, right? Made of tiny particles of silt and clay just suspended in the water.
Exactly. If this area were subjected to large, crashing ocean waves, The kinetic energy of the water would keep all that fine dirt churning, and it would eventually just wash out to the open ocean.
So the sheltered calmness of the water is what allows those tiny particles of dirt to finally lose their momentum, drift down, and settle onto the bottom.
It is an incredibly slow accumulation. Over thousands of years, layer by microscopic layer, that settling mud builds the flat platform of the marsh.
It's basically the ultimate border town. It connects the land and the sea, allowing land animals to wander down to hunt and ocean animals to swim up to feed.
But I want to push back on the optics of this place for a second. If you're just a casual observer or a family driving over a bridge on your way to a beach vacation, it just looks like an endless, monotonous field of grass and mud.
Yeah, it looks completely empty from the highway. You don't see massive herds of animals. You don't see towering trees. So why does this seemingly empty field matter so much?
Well, the emptiness is a total illusion. It looks empty because the residents are absolute masters of hiding.
And they've evolved to be masters of hiding because the physical environment itself is incredibly hostile.
Oh, yeah. The mud and the water are actively trying to kill everything that lives there.
Which sounds crazy, but to understand the survival strategies of the animals, we really have to look at the foundational chemical battle happening in the mud and the plants.
Let's get right into the mud, because we absolutely cannot ignore the sensory reality of it. The smell.
Oh man, the smell. If you have ever rolled down your car window near a salt marsh at low tide, you know exactly what we were talking about.
It instantly hits your nose. That heavy, sulfurous, rotten egg smell. Most people assume they're smelling raw sewage or pollution or hundreds of dead fish rotting in the sun.
But they aren't. That smell is actually the scent of an alien metabolism operating right under our feet.
Right. Because the marsh mud is flooded by the tide every single day, the soil is completely waterlogged. The microscopic spaces between the particles of silt and clay are entirely filled with water.
And because oxygen moves like 10,000 times slower through water than it does through air, the oxygen in that deep mud is quickly consumed and it's never replaced.
It becomes an anaerobic environment, a space completely without available oxygen.
Which is so weird. I'm struggling to square this with basic biology.
Yeah.
Every science class teaches you that soil aeration is critical.
Oh, absolutely. If you overwater a houseplant, the roots rot and the plant dies because the root cells literally suffocate without oxygen.
Right. So if this marsh mud has zero oxygen, how is there an entire biological community thriving down there? By all standard rules, it should be a total dead zone.
That is exactly the puzzle. And the answer is that life finds an alternative chemical pathway. In a normal environment, terrestrial organisms, including us, we use oxygen to breathe and break down our food.
That's highly efficient.
Very. But deep in that waterlogged mud, the specialized bacteria living there are completely locked out of the oxygen supply. So to survive, they have to pivot.
Okay, so what do they breathe instead?
Instead of breathing oxygen, they breathe a chemical called sulfate, which is really abundant in salty ocean water.
Wow.
Yeah, they use a completely different biochemical pathway to strip the oxygen atoms from the sulfate molecules. And when they do this, the waste product isn't carbon dioxide, which is what we exhale. The byproduct is hydrogen sulfide gas.
Hydrogen sulfide. And that is the exact chemical that smells like rotten eggs.
Exactly. So when you are standing on the edge of the marsh, you aren't smelling decay in the traditional sense. You are literally inhaling the exhaust fumes of an ancient anaerobic metabolism.
You're smelling the microscopic breath of billions of specialized bacteria actively working in the mud. That is so cool.
It really is. They are fundamentally altering the chemistry of the soil. Now, imagine being a plant tasked with colonizing that soil.
Oh boy, you're trying to anchor your roots in a thick, pressurized mud that offers absolutely zero oxygen.
And on top of that, you are being submerged twice a day by toxic, salty ocean water.
Right, because salt is a desiccant. It draws water out of living cells. It kills almost every plant on Earth by basically dehydrating them on a cellular level.
If you poured a single bucket of ocean water on a typical suburban lawn, that grass would shrivel and die in a matter of days.
So this is where the true superheroes of this ecosystem step in, the ecosystem engineers. The plants that dominate the salt marsh belong to a category called halophytes.
Halophyte translates directly to salt-tolerant plant. But we need to clarify a massive misconception here. These plants do not actually prefer salt.
Wait, really? They don't like it.
No, the salt is still highly toxic to their cellular machinery. If you take a salt marsh grass and plant it in a freshwater greenhouse, it will grow faster, taller, and stronger than it ever could in the marsh.
Okay, so why live in the marsh then?
They endure the brutal, toxic environment for one strategic evolutionary reason: to escape competition. By evolving mechanisms to survive where nothing else can, they get an environment with zero shade and abundant nutrients entirely to themselves.
That is a brilliant evolutionary trade-off. I'll live in the toxic waste zone, but I get the whole zone to myself.
Exactly. Let's look at the MVP of this ecosystem, a plant called smooth cordgrass. This is the tall, thick, vibrant green grass that completely dominates the low marsh right at the water's edge where the flooding is the worst.
Okay, so how does this specific grass solve the oxygen problem? How does it survive having its roots trapped in that suffocating anaerobic mud we just described?
It solves the oxygen problem by functioning like a biological snorkel.
A snorkel.
Yeah. Inside the tall stems of the smooth cordgrass is a specialized tissue called parenchyma. Instead of being solid, the inside of the stalk is made of a network of hollow, straw-like tubes and air spaces.
Oh, wow.
These tubes run continuously from tiny pores in the upper leaves all the way down the stalk and directly into the root system buried deep in the toxic mud.
So the plant physically pipes its own breathable oxygen from the air down into the anoxic mud.
It maintains a self-contained life support system while buried in alien mud.
That's incredible. But what about the salt? The roots are still surrounded by highly concentrated salt water. It has to drink to survive, but drinking ocean water is a death sentence.
Right, so the plant relies on an active filtration and pumping mechanism. The roots are highly selective about what they let in, but inevitably some toxic salt enters the plant's vascular system.
So how does it not die?
To prevent the salt from destroying its internal cells, the cordgrass expends a massive amount of energy to physically pump those salt ions out of its sap and push them out through specialized glands on the surface of its leaves.
It's actively sweating the salt away.
It really is.
If you ever walk through a salt marsh on a blistering hot, dry summer day and look closely at the blades of the smooth cordgrass, they actually sparkle. They look like they've been frosted.
Yeah, what you are seeing are thousands of tiny, glittering white salt crystals left behind on the exterior of the leaf after the water evaporates.
It's a visual testament to how hard that plant is working to keep its internal chemistry balanced. But I have to say, as cool as the sweating grass is, my absolute favorite botanical survival trick belongs to a completely different plant.
Oh, I know which one you're going to say.
One that lives slightly higher up in the elevation of the marsh. It's called pickleweed.
Pickleweed, or glasswort, is a fascinating specimen. Visually, it abandons the grass aesthetic entirely. It looks like a series of tiny, plump, green, fleshy pickles stacked end to end to form a stem.
And its strategy for dealing with the toxic salt is so dramatic. Unlike the cordgrass that sweats it out, pickleweed is a succulent.
Right. When it takes in salt water, it rapidly drinks up a massive amount of additional water to dilute the salt concentration inside its body, pumping up those little fleshy segments.
But it can't dilute it forever, right?
No. So it actively transports and isolates all of the toxic salt ions into the very top segments of its branches. It uses its highest tips as a biological toxic waste dump.
And then what?
When those specific tip segments reach maximum toxicity and can't hold another drop of salt, they turn a bright, vibrant, almost neon red.
And then the plant just drops them entirely. They just break off and fall into the mud.
It is an extreme, localized form of controlled cell death to preserve the organism as a whole. It safely ejects the toxic material, sacrificing a piece of itself so the main body can survive.
It is exactly like a rocket ejecting a spent, heavy fuel tank, or like a hiker taking off a backpack full of lead weights. Too much salt in this section. Boom, jettison the tip, problem solved. The biology is just wild.
It really is. But the crucial thing to understand is that the implications of these adaptations go far beyond just the plants themselves.
What do you mean?
Well, these plants are not merely surviving in a tough spot. Because they figured out how to exist here, they become the master builders of the entire landscape. This is why we call them ecosystem engineers. They physically manufacture the real estate.
Okay, let's break down the mechanics of that. How exactly does a field of grass physically manufacture land?
It goes back to the tidal water we discussed earlier. When the high tide rushes in from the ocean or the estuary, it brings a massive load of suspended dirt, silt, and organic matter.
Right.
But when that fast-moving water hits the incredibly dense, thick wall of cordgrass stalks, the physics of the water changes. The stems create immense friction.
So the water is forced to navigate around millions of vertical obstacles.
Exactly. And as a result, it rapidly loses its kinetic energy, it slows down, and in fluid dynamics, when water loses velocity, it can no longer carry its suspended load. The dirt simply drops out of the water column and settles onto the mud.
So the entire field of grass basically acts as an infinitely complex biological speed bump. It's a giant net constantly catching dirt from the water.
Precisely, and it doesn't stop there. Below the surface, remember that the mud is anaerobic.
Right, no oxygen.
Because there is no oxygen, normal decomposition is halted. When the vast, thick network of cordgrass roots eventually dies, the organic material doesn't rot away into nothing like it would in a dry forest.
Oh, it just sits there.
It persists. It piles up on top of itself year after year, decade after decade, building a dense, thick, spongy layer of organic soil called peat.
So between the trapped dirt falling from above and the undecomposed roots building from below, the plants are literally jacking up the elevation of the land.
They're fighting inch by inch to keep their heads above the rising ocean.
They are constructing their own city.
Yeah.
And this city, just of mud and roots, operates on a schedule that is completely foreign to us as human beings. We live our lives by the sun, day and night.
But the salt marsh operates on a much more complex, unforgiving timeline, because this entire environment is dictated by the pulse of the tides.
The tides are the heartbeat of the ecosystem. Everything in the salt marsh, when an animal can eat, when it must hide, when it's safe to reproduce, is controlled by the gravity of the earth, the moon, and the sun.
So let's lay out the layout of this city based on that heartbeat. Down at the water's edge, we have the low marsh.
This is the realm of the smooth cordgrass we just discussed. This area gets completely flooded by the tide twice every single day.
But if you walk just a little bit further inland, the elevation of the mud rises by maybe just a few crucial inches. And this creates the high marsh.
The high marsh is a completely different microhabitat because of the tidal math. It does not get flooded every day.
Right. It only goes underwater during the extreme high tides, which occur when the Earth, Moon, and Sun align to compound their gravitational pull. This happens during the full moon and the new moon. We call these massive monthly tidal events spring tides.
So if you live in the high marsh, you have exactly 28 days of relative dryness before the ocean comes roaring up to completely submerge your home. Imagine having your entire life, your safety, your family planning, scheduled by the exact phase of the moon.
And nowhere in the marsh is this incredible pressure more evident than in the story of the salt marsh sparrow. This is a story that feels like an intense, ticking clock thriller.
Oh, I love this bird. The salt marsh sparrow is a remarkable, highly secretive little bird. Its entire evolutionary destiny is tied to this specific habitat. It lives in the salt marsh and absolutely nowhere else on the planet.
It is a small bird with a little orange and buff face, and it makes its living by weaving a cup-shaped nest out of specialized grasses right in the high marsh, just a few inches above the surface of the mud.
But wait, we just established that the high marsh gets entirely flooded by the massive spring tides every 28 days. How can a bird nest on the ground if the ground is guaranteed to go underwater?
Well, it creates a razor-thin window for survival. The mother sparrow is locked in a desperate biological race against the moon's gravity. Her strategy is entirely dependent on perfect timing.
So she has to wait for the water to drop.
She waits until the massive spring tide reaches its absolute peak and begins to drain away. The very second the water recedes, leaving the high marsh exposed, her biological clock starts ticking. She immediately begins weaving her nest.
Wow, so she has a 26-day sprint. Let's walk through this timeline because the urgency is just astounding. Day 1. The water recedes, and she frantically builds the nest.
Day 5. The nest is complete, and she lays her eggs. Now she has to incubate them.
Day 17. The eggs finally hatch, revealing tiny, blind, completely featherless chicks. They are helpless. From this moment on, the mother is working herself to the point of absolute exhaustion.
She is flying constantly back and forth across the marsh, hunting for protein-rich spiders and insects, stuffing food down the throats of her chicks to accelerate their growth.
Because while she's feeding them, she knows the moon is waxing. The tides are creeping slightly higher with every passing day.
Day 22. The chicks are getting bigger, but they still can't fly. The water during the daily high tide is now visibly creeping up the stalks of grass below the nest.
Day 25. The moon is almost full. The gravitational pull is immense. The tide rushes in, and the water is literally splashing against the bottom of the woven nest. The chicks are getting wet.
The mathematics of her breeding cycle demand that by day 26 or 27, those chicks must be physically strong enough to scramble out of the woven cup and climb vertically up the tall grass stalks, clinging to the stems just like the periwinkle snail we described earlier.
If they cannot climb by the time the massive spring tide returns on day 28, the entire nest will be completely submerged and the chicks will drown.
The mother's entire reproductive success is a razor-thin margin of survival dictated entirely by celestial mechanics.
It gives me absolute goosebumps. A tiny bird racing the moon, happening right off the side of the highway in that empty field of grass.
Yeah, but so we have birds utilizing the physical structure of the grass to nest and hide. But this brings up a massive ecological question. We have an entire ecosystem made of lush, green, highly productive grass.
You would assume, logically, that there would be animals everywhere grazing on it, like cows in a pasture or zebras on a savanna.
That is the logical assumption, but the reality of the salt marsh food web is far more complex and bizarre. The truth is that almost absolutely nobody eats the living cordgrass.
Wait, why not? It's literally everywhere.
Because it is incredibly unpalatable and difficult to digest. Remember, it is pumping toxic salt out of its leaves. Furthermore, the physical structure of the plant is heavily reinforced with silica.
Silica, like glass.
Essentially, yeah. It makes it incredibly tough and rigid, it has to be, to withstand the daily battering of the tidal currents. For most herbivores, eating living cordgrass would require more caloric energy to digest than the plant actually provides.
Okay, so if the foundational plant of the ecosystem is basically inedible while it's alive, what fuels this massive biological city? What is everyone eating?
To find the fuel, we have to look away from the living leaves and move into the pantry of rot.
Ooh, the pantry of rot.
The energy transfer in the salt marsh is driven by death and decay. When the tough cordgrass dies back at the end of its growing season in the winter, the stalks turn brown, break off, and fall into the water.
And as these dead stalks float around, the tidal currents and wave action physically smash them into smaller and smaller fragments.
And this is where our microscopic friends make their return.
Right. As soon as the grass breaks into tiny pieces, it is rapidly colonized by an immense army of microscopic fungi and specialized bacteria, including the sulfate-reducing bacteria we talked about earlier.
These microbes possess the specific enzymes required to break down the tough cellulose and silica structures of the dead grass.
So this mixture of tiny fragmented dead plant bits, heavily coated in a rich, living layer of bacteria and fungi, is called detritus. It is essentially a magical, nutrient-rich biological soup.
Detritus is the fundamental base-level fuel for the entire salt marsh food web. Think of it like a cracker covered in peanut butter.
A cracker with peanut butter.
Yeah, the dead piece of grass is the cracker. It provides a physical surface but isn't particularly nutritious on its own. The bacteria and fungi growing on it are the peanut butter. They are packed with rich proteins, lipids, and calories.
I see.
When the marsh animals eat the detritus, they are primarily digesting the rich microbial peanut butter and excreting the cracker back out to be colonized all over again.
That is a perfect analogy. We go from a bird racing the gravity of the moon to an entire ecosystem running on a soup of dead grass and bacteria. Let's look at the residents living on the ground floor of this city, the animals whose entire existence revolves around eating this detritus. I want to talk about the fiddler crabs.
Oh, fiddler crabs are the excavation crew of the marsh. They are small, incredibly active crabs that live in massive colonies on the mudflats.
The males are instantly recognizable because they possess one massively oversized claw that they wave back and forth, right? Like they're playing a fiddle.
Which they use to court females and defend their tiny territories. But while the giant claw is for show, their real ecological work happens with their smaller feeding claw.
Right. If you watch them at low tide, it looks like a microscopic assembly line. They use their small claw to rapidly scoop up small clumps of mud, bringing it constantly to their complex mouth part.
They meticulously scrape off all that delicious bacteria-covered detritus, swallow the microbes, and then they physically roll the leftover clean mud into neat, perfectly round little spheres.
And they toss these mud balls to the side. If you look closely at the marsh mud at low tide, the entire surface is carpeted in thousands of these tiny mud balls. It looks like the discarded pieces of miniature snowmen.
It is a massive landscape-level cleaning operation, but the act of eating is only half of their impact. To hide from predators and the incoming tide, fiddler crabs dig deep, complex burrows down into the mud.
And these tunnels provide a massive critical service to the ecosystem, don't they? They act as vital ventilation shafts.
Exactly, because the mud is anaerobic.
Ooh. Remember how the cordgrass has to pipe oxygen down to its roots because the mud has none?
Yes, the massive network of fiddler crab burrows artificially increases the surface area of the mudflats, allowing highly oxygenated surface water and air to penetrate deep into the otherwise anoxic ground.
So this aeration actually helps the cordgrass roots survive and grow more efficiently. It is a brilliant unintentional partnership.
The grass provides the dead leaves to create the detritus the crabs need to eat, and the crabs constantly till and aerate the soil so the grass can thrive.
It's incredible how tightly woven these relationships are. But here is where the story gets really bizarre. Let's return to our friend from the very beginning of the story, the marsh periwinkle snail.
The tiny little guy desperately climbing the grass stalk to escape the blue crab.
Yeah, you were telling me that these snails don't just climb the grass to hide, they're actually agricultural farmers.
It is genuinely one of the most remarkable and complex behaviors observed in the salt marsh ecosystem. The periwinkle snail spends a lot of its time on the stalks of the living cordgrass.
Like most snails, it possesses a radula, right? A rough, ribbon-like tongue covered in microscopic teeth.
But it isn't using its radula to simply graze on the grass because, as we established, the living grass is too tough and salty. Instead, the snail uses its tongue to deliberately chew longitudinal grooves, long, damaging physical cuts directly into the tissue of the living cordgrass stem.
Okay, so it's intentionally plowing a field on the side of a plant stem.
Yes, and it gets more specific. After making these cuts, the snail physically defecates directly into the open wounds it just created.
Gross, but effective.
The snail's feces acts as a highly potent, nitrogen-rich fertilizer. This precise, deliberate combination of an open, damaged plant wound combined with targeted fertilizer creates the perfect microenvironment for a very specific type of wild fungus to bloom.
This completely upends how we think about invertebrate intelligence. You have tiny snails driving their little biological tractors up a blade of grass, deliberately wounding the plant, fertilizing their crops, and operating highly specialized agricultural fungus farms.
They are farming. Once the cultivated fungus blooms and spreads within the cuts, the snail returns to the site and harvests it. It eats the rich, easily digestible, highly nutritious fungus instead of struggling to digest the tough, salty grass itself.
That is just mind-blowing. Nature finds the most inventive, convoluted ways to extract calories.
Yeah.
But there is a dark side to this farming operation, isn't there? This isn't a completely peaceful coexistence.
It definitely is not, and it highlights a critical concept about ecological balance. The snails are farming the grass, but to do so, they have to physically damage the plant.
Right.
Under normal conditions, this low level of parasitism is fine. The vast fields of cordgrass can easily tolerate a few snail cuts, and the reason the damage stays minimal is because of top-down predation.
Predators, like the blue crabs swimming in with a high tide, or diamondback terrapins patrolling the creeks. They aggressively hunt and eat the periwinkle snails, keeping their population numbers carefully in check.
The snapping blue claws from our opening. The crabs are essentially the marsh police, patrolling the stalks and preventing the farmers from getting out of control.
Exactly. But here is where human interference can completely unravel the system.
Yes. If humans aggressively overfish the blue crab populations in the adjacent ocean, or if the terrapins disappear due to boat strikes or habitat loss, the periwinkle snail population loses its primary predators.
And the snail population explodes exponentially. Suddenly, you don't have a few snails managing small farms. You have massive, uncontrolled armies of thousands of snails, all frantically chewing deep cuts into the grass, trying to farm enough fungus to survive.
Too many farmers, and not enough land to sustain the damage.
And the result is catastrophic, isn't it?
An overpopulation of snails can inflict so much mechanical damage and fungal infection that they can actually kill the cordgrass entirely. An unchecked snail population can chew down a healthy, vibrant, land-building marsh and reduce it to a barren, rapidly eroding mudflat in a matter of a few seasons.
Wow. It perfectly illustrates how delicately suspended the food web is. The survival of the entire geographic landscape relies on a blue crab eating a snail.
Everything is fundamentally tethered together. The detritus feeds the crabs, the snails farm the grass, the blue crabs eat the snails.
And the mention of the blue crabs brings us to a massive shift in how we view the marsh. Because blue crabs don't live in the high marsh mud all the time. They commute.
Which opens up the incredible reality that the salt marsh is famous globally for being the ultimate ocean nursery.
This is arguably one of the most vital biological functions of the salt marsh on a planetary scale, right?
Absolutely. If you think about the open ocean from the perspective of a newly hatched 2-inch long baby fish or a juvenile shrimp, It is a terrifying, highly lethal environment. The open water is a three-dimensional hunting ground with absolutely zero cover.
There's nowhere to hide from larger, faster predators. But the coastal salt marsh provides a structurally complex physical sanctuary.
Let's visualize how this works mechanically. Imagine you are a juvenile striped bass or a tiny, vulnerable baby blue crab. You are out in the estuary, and the tide begins to rise.
You ride that swelling water up out of the deep channels and onto the flooded platform of the marsh. Suddenly, your environment transforms.
You are no longer in open water. You are swimming through a dense forest of millions of thick, stiff, vertical cordgrass stalks. It is an infinitely complex, three-dimensional maze.
If a massive open ocean predator like a 6-foot adult shark or a huge bulky grouper tries to follow you in, it physically cannot maneuver. Its large body would simply get wedged and stuck in the dense matrix of grass stems.
So the juveniles are granted an immediate physical refuge. And it's not just a hiding spot, it's a heavily stocked pantry.
Because of all that rich bacterial detritus we just spent time detailing, the water flooding the marsh is thick with microscopic plankton, tiny worms, copepods, and abundant food perfectly sized for baby fish and crabs to eat.
It is a warm, highly protected, all-you-can-eat buffet that accelerates their growth.
But the heartbeat of the tide is relentless. The buffet doesn't stay open all day, the water doesn't stay high forever. And this is where the daily migration becomes a highly dangerous, high-stakes game of hide and seek.
When the tide peaks and begins to fall, the water rapidly drains off the flat platform of the marsh. The small fish, shrimp, and crabs must be hyper-aware of these changing hydrodynamic cues.
They have to realize the water depth is dropping and quickly ride the receding currents back out of the grass maze and into the deeper, muddy channels, the tidal creeks.
If they miscalculate or get trapped in a depression, they will be left stranded high and dry on the mud when the water vanishes, and they will rapidly perish in the sun.
But retreating into the tidal creeks isn't exactly a safe trip home, is it? Because guess exactly who is waiting in that deeper water.
The larger predators. The adult fish that were too large to enter the grass maze are not stupid. They understand the mechanics of the tide perfectly.
They stage themselves at the mouths of the tidal creeks and simply wait. They let the falling tide act as a conveyor belt, flushing a massive feast of small, retreating fish right into their waiting mouths.
It's an intense daily migration fraught with peril on both sides. You have to risk the gauntlet to get the food, but incredibly, not all the fish retreat.
Some of them choose to stay behind on the draining marsh. We have to talk about the mummichog, because this fish might be the most biologically resilient vertebrate on the planet.
The mummichog is a fascinating, incredibly tough resident of the marsh. It is a small, stout killifish. When the tide drains away, instead of fleeing to the dangerous predator-filled creeks, the mummichog often deliberately stays behind.
It allows itself to become trapped in tiny, highly shallow puddles of water left behind on the surface of the mud, which are known as pans.
Let's think about the physics of a shallow puddle of water sitting on dark mud in the middle of a July afternoon.
The sun is absolutely beating down. Because the puddle is so shallow, the water temperature skyrockets, easily reaching over 90 degrees Fahrenheit.
And because the water is evaporating in the heat, the concentration of the salt spikes drastically, becoming far saltier than the open ocean.
And because the water is hot and stagnant, it loses its ability to hold dissolved oxygen.
It becomes a hot, hypersaline, anoxic trap. A normal fish, say, a trout or a bass, would go into acute physiological shock and perish within minutes in those conditions.
But the mummichog has evolved extreme metabolic flexibility. To survive the heat and the lack of oxygen, it can actively depress its metabolism, drastically lowering its need for oxygen.
It alters the function of its gills to cope with the extreme salt concentration. It essentially powers down its biological systems and just waits it out in these harsh little hot tubs until the next high tide returns to free it.
And while it waits, it feasts on the mosquito larvae that also inhabit the puddles. It is practically indestructible.
But surviving the water chemistry is only one part of the battle, because if you are stuck in a clear, shallow puddle, you are highly visible from above.
And the marsh is relentlessly patrolled by some of the most elegant, patient, and lethal avian hunters in the world.
We are talking about the wading birds. The great egrets, the great blue herons, the white ibises. These birds are specifically adapted to exploit the shallow water of the marsh.
If you have ever watched a great egret hunting in the shallows of a tidal creek, it is mesmerizing. It looks like a tall, brilliant white marble statue. It stands perfectly, absolutely motionless in the water for incredibly long periods.
Why? because it understands the physics of water. Any sudden movement, any tiny ripples sent across the surface will alert the mummichogs and the crabs to its presence, and they will vanish into the mud.
So the egret waits. It locks its eyes on the water, completely frozen, until an unsuspecting fish or crab swims right over its toes, and then, bam! The neck muscles release and the sharp beak strikes downward with the speed of a lightning bolt.
It is a masterclass in kinetic energy and patience, and the avian predators are joined by some highly intelligent mammals as well.
Like American minks, which are fiercely fast and agile swimmers, will dart through the high marsh grasses, aggressively hunting for crabs and rodents.
And in the deeper tidal creeks of certain marshes, particularly in the American South, you can witness some highly sophisticated, coordinated hunting by bottlenose dolphins.
Oh, the dolphin strand feeding. This is incredible. Dolphins are renowned for their intelligence,
Yeah.
and they have figured out how to use the specific geography of the muddy tidal creeks to their advantage.
A pod of dolphins will swim up a narrow creek, and working together as a highly coordinated team, they will deliberately herd a school of fish up against the steeply sloping mud banks.
Once the fish are trapped against the wall, the dolphins create a massive bow wave that washes the fish completely out of the water and up onto the exposed mud.
And then the dolphins will actually launch their massive, heavy bodies out of the water entirely, hydroplaning on their sides up onto the slick mud to snap up the stranded fish before forcefully wiggling their bodies back down the slope and into the safety of the water.
It is a stunning, highly risky, culturally transmitted hunting strategy.
And it truly showcases the immense biological diversity and behavioral complexity that the marsh supports.
We have touched on an incredible array of life snails, crabs, resilient fish, racing birds, and hydroplaning dolphins. But at this point, we have to pivot and answer the ultimate so what question.
Why does this intricate web of life, this muddy nursery, actually matter to us? Why should a listener, perhaps living hundreds of miles inland, care about a baby fish hiding in a field of cordgrass?
Here is the mind-blowing statistical reality that connects the mud to your life. Over 75% of the commercially important fish and shellfish species, the seafood that ends up on our dinner plates, the species that support massive, multi-billion-dollar global industries and provide vital protein for billions of human beings, spend at least some critical portion of their early lives hiding and feeding in these coastal salt marsh nurseries.
We are talking about the foundational pillars of the global seafood economy: shrimp, flounder, blue crab, sea trout, striped bass, oysters.
If we were to systematically destroy the coastal salt marshes, the ocean fisheries would effectively collapse. The safe havens would be gone, the immense detritus food source would vanish, and the juvenile populations of those species would simply not survive the gauntlet of the open ocean long enough to reach adulthood and reproduce.
It is a completely invisible but unbreakable lifeline, connecting that smelly, muddy field of grass directly to the stability of the entire global food supply.
And that realization leads us perfectly into our next major section. We have spent this entire time marveling at what the marsh does to support its animal inhabitants. Now, we need to talk about what this incredible ecosystem does for the physical infrastructure of the planet and for human society. Let's look at the superheroes of the coast.
In the scientific and economic communities, we refer to these as ecosystem services. This is the formal term for the highly valuable, tangible benefits that human beings receive entirely for free, simply by allowing a healthy, functioning ecosystem to exist.
And when you run the numbers, salt marshes are arguably some of the most economically and physically valuable real estate on Earth when it comes to the services they provide.
I think the best way to conceptualize these dense scientific terms is to think of the salt marsh as a superhero possessing three highly distinct world-saving powers.
Superhero power number one, the giant sponge and shield. Let's set the scene. Imagine a massive Category 4 hurricane is churning out in the open ocean. It is generating immense wind, but more dangerously, it is pushing a massive, solid wall of ocean water, a storm surge directly toward a populated coastal town.
If that town is built right on the edge of a flat, sandy beach, the physics are terrifying. That deep, fast-moving wall of water has zero physical obstacles to slow it down. It crashes directly into the seawalls, the roads, and the houses with unmitigated, catastrophic kinetic energy.
But if that same town has the geographic fortune of having a wide, miles-deep, healthy salt marsh situated between the ocean and its infrastructure, the outcome changes drastically. As that rushing, highly destructive wall of storm surge water leaves the ocean and hits the leading edge of the marsh, it encounters millions upon millions of thick, stiff, resilient cordgrass stalks.
It hits the biological speed bump we talked about earlier.
Exactly. The physical friction generated by the water attempting to force its way through that endless maze of vegetation is immense. The grass physically disrupts the hydrodynamics of the wave, bleeding off its speed and fracturing its destructive energy before it ever reaches the solid land.
And while the grass is slowing the wave down, we have to look down at what is happening under the water. Remember the peat, that thick, deep, undecomposed layer of roots and organic soil.
The giant sponge.
Right. Because the peat is highly porous and structured, it acts remarkably like a massive absorbent sponge. A single acre of healthy established salt marsh can rapidly absorb and hold roughly 1.5 million gallons of floodwater.
To put that in perspective, that is the volume of more than 2 full-sized Olympic swimming pools, instantly soaked up and temporarily stored by just one single acre of mud and roots, keeping that massive volume of water completely out of people's living rooms and off the highways.
It is a multi-billion-dollar self-repairing flood mitigation system that we get for completely free. Superhero power number 2 is equally vital, but it focuses on water moving in the opposite direction. Power number 2, the coffee filter.
Water doesn't just assault the coast from the ocean, it also flows heavily from the land down to the sea. When it rains heavily, water runs off our impermeable surfaces, our paved streets, our massive agricultural farms, and our fertilized suburban lawns.
This runoff gathers a massive load of pollutants, heavy metals, spilled motor oil, excess nitrogen from fertilizers, and thousands of tons of loose, heavy dirt. It carries all of this directly toward the ocean.
But before that toxic, muddy river can hit the pristine open ocean, it usually has to pass through the transitional zone of the salt marsh. And here, the marsh acts as a massive, highly efficient biological filtration system.
As the dirty water flows slowly through the dense network of plant stems, the heavy dirt and sediment are physically trapped and settle into the mud. Furthermore, the complex root systems of the plants, along with incredible filter-feeding animals like ribbed mussels and oysters that live in the mud, actively pull those chemical pollutants out of the water column.
They can lock away heavy metals in the soil and absorb the excess fertilizer to fuel their own growth.
The marsh is literally scrubbing the water clean. This is vital because if the marsh wasn't there acting like a giant coffee filter, all of that murky, chemically polluted water would flow straight out into the shallow ocean.
It would completely block out the sunlight, smothering the delicate, highly valuable underwater seagrass meadows, and it would suffocate coral reef systems that require crystal clear, low-nutrient water to survive.
It is the kidney of the coast. Which brings us to the third, and in the context of our modern world, perhaps the most globally significant superhero power of all. Power number 3, the climate vault. In the scientific community, this process is referred to as blue carbon.
We hear a massive amount of well-deserved discussion about planting trees to combat global climate change. We learn that terrestrial forests act as the lungs of the Earth, breathing in atmospheric carbon dioxide during photosynthesis and storing it in their trunks and branches.
But when we look at the raw data of carbon sequestration over long geological timescales, the humble salt marsh actually puts the mighty tropical rainforest to shame.
Okay, let's unpack the biochemistry of that because it sounds counterintuitive. How can a field of grass outperform a towering rainforest?
The secret lies entirely in the decomposition process. When a massive tree in a terrestrial forest dies, it falls to the ground. Because the forest floor is exposed to the air, oxygen is abundant. Fungi, bacteria, and insects immediately begin to consume the wood using aerobic respiration.
As they break the tree down, a massive percentage of the carbon that the tree stored over its lifetime is metabolized and released back into the atmosphere as carbon dioxide gas. It's a rapid cycle of capture and release.
But the marsh operates under completely different chemical rules. We already established that the mud in a salt marsh is completely anaerobic. It has zero oxygen.
Exactly. When the marsh grasses breathe in massive amounts of carbon dioxide from the atmosphere to fuel their rapid growth, they send a large portion of that carbon down into their expansive root systems. When those roots naturally die, they are already buried in that oxygen-free mud.
Because the bacteria down there have to use the slow, inefficient sulfate reduction pathway we discussed, the organic material does not rapidly decompose. It turns into that dense layer of peat.
It is a biological vault. The marsh is physically vacuuming greenhouse gases out of the atmosphere, locking them into solid organic matter and burying them deep in an oxygen-free vault where they cannot escape back into the air.
And the rate at which they do this is staggering. Studies show that coastal salt marshes can capture and bury carbon at a rate up to 10 times faster than a mature terrestrial tropical rainforest. 10 times faster.
It forces a massive paradigm shift in how we value these landscapes. It directly challenges the historical, deeply flawed viewpoint. For centuries, humans looked at salt marshes and saw absolutely nothing of value.
They saw useless, foul-smelling, mosquito-infested wastelands that stood in the way of progress. The standard operating procedure for decades was to drain the water away, fill the marsh with massive amounts of imported dirt, and pave over it with concrete to build lucrative waterfront housing, ports, and highways.
We now realize with terrifying clarity that by paving over them, we were actively destroying our most effective, multi-billion-dollar biological shields and dismantling our most powerful natural climate cooling machines.
Which brings us to a highly difficult but absolutely necessary discussion regarding the future. We've established how complex and vital they are, so we have to examine the threats. What is currently actively destroying the marsh today? We call this phenomenon the coastal squeeze.
To understand the squeeze, we have to look at the intersection of natural geology and human infrastructure. Sea level rise is a reality, and historically, over thousands of years, salt marshes knew exactly how to handle a rising ocean.
They are dynamic systems. As the sea level slowly rose, a healthy marsh would simply migrate backward. It would slowly march inland, retreating to slightly higher, drier ground, maintaining its perfect elevation relative to the tides. We call this natural process transgression.
But here's where the squeeze happens. Imagine the marsh reacting to our rapidly rising oceans, attempting to slowly walk backward away from the incoming water. But right behind the marsh, human beings have decided to build a massive, immovable, concrete seawall to protect a neighborhood.
Or we've laid down a raised, heavily trafficked coastal highway. The marsh attempts to migrate inland, but it bumps directly into our immovable wall. It has absolutely nowhere to go.
It becomes physically squeezed between the rapidly rising ocean on one side and the immovable concrete barrier on the other. Because human infrastructure prevents it from retreating inland, and because the ocean water is rising far faster than the plants can trap sediment to build their mud platform higher, the geometry fails. The water gets too deep, the cordgrass completely drowns, and the marsh collapses into open, barren water.
It is a heartbreaking mechanical failure of the ecosystem. And it isn't just physical displacement they're fighting. They're also fighting intense biological invasions.
We have to mention a plant called the common reed, scientifically known as phragmites.
Phragmites is a highly aggressive invasive species in many coastal regions. It exploits areas where human activity has disrupted the natural hydrology or added too much freshwater and fertilizer pollution. It is an absolute monster of a grass, routinely growing up to 15 to 18 feet tall.
Imagine a wall of grass the height of a two-story building. Because it grows so tall and incredibly dense, it forms these towering, impenetrable walls that block out all the sunlight, completely shading out and killing our native short cordgrass. And because the stalks are so tightly packed, it destroys the intricate network of tiny puddles and creeks that the baby fish and crabs use as a nursery. It turns a highly diverse three-dimensional city into a biological desert, consisting of a single towering weed.
So when we look at the compounding pressures of rising sea levels, rigid human infrastructure causing the coastal squeeze, and aggressive invasive species, it paints a very grim picture. It forces us to ask, what does this all mean for the future? Are we just going to lose these incredible systems entirely?
If you live near the coast, or if you simply rely on the global seafood supply or care about carbon in the atmosphere, that is the ultimate question. We're just going to stand by and watch these incredibly complex, life-sustaining cities slowly drown beneath the waves.
The hopeful, actionable perspective is that the scientific community is not standing still. Our understanding of hydrology and ecology is advancing rapidly. Humans are finally learning from the marsh itself. We are learning how to become proactive ecosystem engineers alongside the cordgrass. We are actively stepping in to manipulate the physical environment to save them.
Let's talk about some of these interventions because the engineering is fascinating. Tell me about the strategy called thin layer placement. I think this is such an elegant solution to a massive physical problem.
It directly addresses the problem of drowning marshes. If a specific area of marsh is trapped by a seawall and the water is rising too fast for the plants to build their own mud, scientists can actively intervene to artificially raise the elevation.
They utilize heavy machinery to take clean mud and sediment that has been dredged from nearby shipping channels, dirt that normally would just be dumped offshore. They pipe the sediment in as a slurry and carefully spray a very thin, perfectly calculated layer of it directly over the struggling marsh surface.
It is exactly like using a spatula to add a fresh, perfectly even layer of frosting to the top of a cake.
That's a great visual. By adding just a few crucial inches of new sediment, it instantly raises the elevation of the marsh floor relative to the tide. It pulls the plants out of the drowning zone, giving the stressed cordgrass the physical boost it desperately needs to keep its leaves above water, oxygenate its roots, and start growing vigorously once again. It buys the marsh precious time.
And we are also addressing the hydrology through manual labor. In areas where the water is getting trapped on the high marsh and suffocating the plants, conservationists are literally digging tiny, shallow, highly engineered channels called runnels.
These act like miniature drainage ditches to help stagnant hot water drain off the surface so the plants don't rot. We are essentially doing the exact same job as the fiddler crabs, manually aerating and draining the marsh. We are finally transitioning from viewing the marsh as a swamp to pave over to viewing it as a critical infrastructure partner. We are working with the physics of the ecosystem instead of fighting against it.
It represents a massive shift in human perspective. We are finally recognizing, quantifying, and respecting the fact that we need the salt marsh for food, for protection, for climate stability, just as much as the marsh now needs us to actively manage and protect its space in a changing world.
What an absolutely incredible, complex journey this has been today. We started our story at the microscopic level, visualizing a tiny snail clinging desperately to a single blade of grass trying to outrun the tide. And we have steadily zoomed out layer by layer to reveal a massive, interconnected, highly engineered biological city.
We have completely dismantled the illusion of the empty field. We have seen that the salt marsh is driven by the vast celestial gravitational pull of the moon. We have learned that its massive food web runs entirely on a magical microbial soup of dead grass.
It serves as an intricate three-dimensional fortress for the vulnerable young of the ocean and acts as an unparalleled physical champion, absorbing the devastating energy of storms and locking away the carbon warming our atmosphere.
It is the ultimate borderland of survivors. You have the smooth cordgrass actively sweating out toxic salt, the mummy chog slowing its heart rate to endure boiling, oxygen-starved puddles, and the saltmarsh sparrow frantically racing the lunar cycle to launch its chicks into the canopy. The adaptations are simply endless.
Now, before we go, I want to leave you with one final brand new thought to mull over. Throughout this entire journey, we've talked about the incredible alien chemistry happening in that dark, oxygen-free mud.
We've discussed how billions of specialized bacteria have been locked in a chemical arms race for millions of years, utilizing alternative metabolic pathways and producing compounds like hydrogen sulfide just to survive the intense competition and extreme conditions.
Think about human medicine for a moment. Historically, we have spent billions of dollars trekking into the deep, pristine tropical rainforests, or sending submersibles into the deep ocean trenches, desperately searching for rare plants or creatures that might yield the next major medical breakthrough or the next powerful antibiotic.
But what if we are looking too far away? Consider the sheer, brutal density of microscopic warfare happening in the extreme, hypersaline, anoxic mud of the salt marsh. Those bacteria have evolved defensive chemicals and toxins that exist nowhere else on Earth.
It is highly probable that ancient, completely undiscovered classes of antibiotics or revolutionary medical compounds are currently sitting in that foul-smelling mud, actively being deployed by microbes right now. The cure for our next major global superbug might not be hiding in an untouched rainforest canopy. It might be quietly trapped in the smelly, sulfurous mud directly behind your local beach highway, just waiting for us to understand it.
It's a profound thought. It proves that there is always more to learn, and that immense value often hides in the places we traditionally dismiss as unpleasant.
Exactly. So the very next time you visit the coast or drive your car over a bridge spanning a wide estuary, do me a favor. Roll down your window. When the coastal breeze inevitably brings you that heavy, strange, sulfurous, rotten egg smell of the marsh mud, don't scrunch up your face. Don't plug your nose.
Understand the incredible, complex machinery you are truly experiencing.
Take a deep, deliberate breath. Because you aren't smelling rot or pollution. You are actually smelling the active exhaust of an ancient microscopic city working in the dark. You are smelling the very breath of a living shield, hard at work, protecting the entire planet. Thank you so much for listening. We'll see you next time on Saltwater Stories.